Good day, grade 12 learners. Welcome to today's technical science lesson. My name is Musa Zulu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Cyborg Discovery Center. All right, today, grade 12 learners, for our third lesson, we are still doing mechanics. Our knowledge area is still mechanics, and our topics of interest today will be impulse and momentum. So we'll be doing impulse and momentum. You remember that last week we started on momentum, talking about the momentum of an object and the change in momentum of an object, how the momentum of an object changes. So this week again, we'll still be talking about momentum, but today we're going to be talking about momentum with impulse. So this should show us how important momentum or how big momentum is for us, grade 12. So it is very, very important that it is a concept that we all understand because it is big and it's going to be carrying a lot of marks in your final examination. So understanding momentum becomes very, very important in that case. Right. So again, we are still doing paper 1, and the structure of paper 1, as we've looked at before, is that paper 1 consists of 2 sections. That will be section A and section B. Section A usually has 10 multiple choice questions worth about 20 marks. Sometimes it will also have matching items, which will be about 8 marks. Section B has structured or long questions, which if we only have multiple choice questions on section A, then section B will be out of 130 marks. But if we also have the matching items on section A, section B will be about 122 marks. The total marks for the paper 1 is 150 marks, and the duration is 3 hours. It is extremely important that we always understand the structure of the paper and we know what to expect in our paper, grade 12. For example, the topic that we are doing today is on paper 1, and it is usually question 3 or question 4, depending on the paper. So it's important that we know on which question and what concept we need to expect there. So when we're talking about momentum and impulse, we expect it up around question 3 or question 4 of the question paper, and it carries a lot of marks. So it is very, very important that we understand it. All right. Our formulae focus for today, we're still again on table 2 formulae. And here for today, we are going to be focusing mostly on these 2 formulas, right? We're going to be focusing on these 2 formulae. That will be F net delta T is equals to delta P, and delta P is equals to MVF minus MVI. You would remember that we looked at this one last week as the change in momentum of an object. So today we'll be simply adding this one, trying to understand if there is a relationship between change in momentum and F net delta T, which in this case we'll say is impulse. Okay. So before we dive into it, grade 12, I want us to think, you would maybe agree with me here that in the olden days, when we looked at cars, right, we would find that in cars of the olden days, these cars used to be rigid, right? So maybe, or I would say strong. These cars used to be strong or rigid. For example, I have a picture here of a Toyota Cressida, an old Toyota Cressida, right? If you could lean against an old Toyota Cressida, you'd realize it's a rigid car. You can lean against it easily, right? It has a very, very strong make. Its body is made up of strong parts. You can lean against it easily. It gives you that sense, right? However, if you look at the new cars, right? The new cars, nowadays cars, even if you look at how they are designed, look at them here. They look like they are weak cars, right? They are not that rigid. They are not that strong, right? So this, when I realized it, it used to raise a question to me to say, why are nowadays cars weak? Why are they made up of material that is weak, that if you lean against this car, for example, let's say you just sit here, you can simply dent it. You can simply dent it by just sitting against it or leaning against it. The new car will be dented. But this is not going to happen on an old Toyota Cressida, but it will happen in this new Polo. You can dent it by just simply sitting it. So the bonnet is weak, the bumper is weak, right? Even the fenders also, they are weak, unlike the old cars. I used to ask myself, why is that the case? Is it because they are trying to be economical? Are they trying to save money with this? Until I did the research and I find out which that is not the reason. It's not that they are trying to save money. So today we are going to be trying to find out why is it that these nowadays cars are now weak compared to the olden day cars. Okay, the concept, to understand it, I will start by trying to make an example here. What if I have 2x? Let's use this example to try and understand the concept of why these cars are not as rigid as the olden day cars. What if I have an egg, right? Egg 1 and egg 2, okay? And I want to drop these 2 eggs. I want to drop them from the same height. So holding them from the same height, and I let them go. But now the difference with these 2 eggs is that one of the egg is going to be crashing, right, on the floor, right? A hard floor for that matter. It's going to be crashing on the hard floor surface, right? And then the other egg, I'll let it fall on top of what? On top of a cushion, right? So I let both of them fall. The other one is going to fall on the floor. The other one is going to fall on the cushion. Okay, what's going to happen? Well, as the picture clearly shows us here, the egg that falls on the floor is definitely going to do what? It's going to break. While the egg that falls on the cushion, chances are it's not breaking. And the question is why? Why is the other one breaking and the other one not breaking? Because the 2 eggs were dropped at the same height, meaning they had the same initial velocities. They should be having the same final velocities as well. So why is the one dropping and the other one not dropping? Well, a simple and clear reason to that is that, well, the other one is dropping to the floor and the other one on the cushion. Well, but if you answer me like that, you haven't actually answered me, because I want reasons as to why is it that when it drops on the cushion, it does not break, and why is it that when it drops on the floor, it breaks. So we need to scientifically answer that question. Try to find out what is the cause here, right? Okay, so one thing we should realize is that when these eggs reach the floor, they are going to experience a force, right? When they reach the ground and the other one reaches the cushion, they are going to experience a force that is exerted on the 2 eggs, right? So by this one breaking, it is clear that the force that this one exerts is greater than the force that the other one experiences. So the force that this one experiences is smaller, right? Smaller force that this one is experiencing, right? By it not breaking, it's a clear indication of that the force that it experiences is smaller, and the force that this one experiences is what? Is greater. But then again, that is not enough. Why? What causes this force to be smaller? While they had the same initial velocities and now they're having the same final velocities. Then what causes the force here to be smaller? It is said that all of this is based on something called the time of contact. How long it takes for this egg or each of these eggs to come to a complete stop. Because what is happening is that you let go of the eggs, right? They are going to come to a complete stop. So the question is, how long does it take for each of these eggs to come to a complete stop? For this one, it will take a very, very small amount of time. It will take a small amount of time for it to come to a complete stop. It is coming, it is falling against a hard surface. So it comes to a stop very, very quickly. So the time it takes for it to come to a stop is very, very quick. While this one that falls on the cushion, the time for it to come to a complete stop sort of increases. It does not just simply stop like the one that falls on a flat surface, right? It falls, and the cushion allows it, sort of cushioning it, allowing it to continue, but while decreasing speed over time. So that means for it to eventually come to a complete stop, it takes more time compared to the other one. So there is more time for this egg to come to a stop. Well, Once there is high time, right, that is taken by the egg to come to a stop, turns out that this decreases. It then decreases the force that is exerted on the egg. So the amount of time that the egg takes to stop, turns out that this will decrease the what? The force exerted on the egg. While if the time that the egg takes to stop is small, then that will increase the force that is exerted on the egg, which is the reason as to why this egg is going to break, the reason as to why this egg experiences a greater force compared to the other one, because the other one is going to have a larger amount of time that it will take for it to come to a complete stop, while the other one takes a very, very small amount of time to come to a complete stop. This increases the force acting on the egg, right? We're talking about eggs, but then this concept that we're talking about here is important, because this is the very same concept that, if we think about it, is maybe the reason why these cars that we talked about in the previous slide, that now they are now soft. They are not as rigid as the cars in the olden days. But before we talk about them, let's continue there. So this concept of where we are talking about the force and the amount of time is referred to as the impulse on an object. So it's very important that grade 12 we are able to define this concept, right, as part of our knowing the examination guideline and as part of knowing the things that can be examined, right? This impulse definition is examinable. We must be able to know it, must be able to define. So we define impulse as the product of the net force acting on an object and the time the net force acts on that object. So what are we looking at? We are looking at the net force that is acting on an object and what? And the time that that net force acts on an object. Those two things are important for what? For the impulse, for us to know the magnitude of the impulse on the what? On the object. So basically, we are going to be saying that while the other egg was falling on the floor, it had greater impulse than the object that was falling on the cushion. So, and when we say it had greater impulse, what are we talking about? We are talking about the product between the force that was exerted, the net force actually that was on it or exerted on it, and the time, right, that net force was acting. So if the net force acts for a small amount of time, then it's expected that the egg is going to break. But if the net force acts for a large amount of time, then it is expected that the egg is going to what? Might not break. It is a little bit safer for it. Okay, so this impulse can be represented mathematically by the formula impulse is equal to F net delta t, or F net multiplied by delta t. Hence, we are saying the product, right? So from the formula itself, I can remind myself of the definition, because in maths, when you multiply two things, you get the what? The product. The answer that you get when you multiply a 1 multiplied by 1, that one that you get as your answer is called the product. Hence, we are saying if I multiply the net force with the change in time, what I get is the product. It's the product of what? It's the product of the net force acting on an object and the time that the net force acts on an object. So mathematically, it is represented by the formula impulse is equals to F net delta t, where the F net is standing, as we have seen from the previous lesson. F net represents the force. It is the sum of the forces that are acting on an object, and the force is measured in newtons as the SI unit, while the delta t represents the what? The time, and the time is measured in what? The time is measured in seconds. So if you look at F net delta t as the force in newtons and the time in seconds, then you can come up with the SI unit for impulse, to say the SI unit for impulse is Newton second. Grade 12, I would like to warn you here, because a lot of you tend to forget this SI unit. A lot of you, because impulse as a question is not regularly asked, a lot of you tend to forget this SI unit. A lot of you start using a different SI unit. So I would like to warn you that let's not forget this SI unit. Let us not forget this SI unit. From the formula itself, let us try and remind ourselves of the SI unit of the impulse, for the fact that we are multiplying the F net and the delta T, the newtons and the seconds. The SI unit for impulse is Newton second. This is the formula that you are expected. This and only this is the formula that you, as a grade 12 learner doing technical science, expected to use whenever you are asked to either calculate or determine the impulse on an object, N as Newton second. Okay, so impulse, grade 12, is a vector quantity. As we said in the previous lesson that momentum is a vector quantity. Impulse is also a vector quantity. And when we say impulse is a vector physical quantity, what does this mean? This means that impulse has magnitude and direction. Very, very important. I'm raising it as an awareness again. It's very, very important that we remember that it has magnitude and direction. So you're not going to determine impulse, do the calculation, get your answer, and then you leave it maybe, for example, as 15 Newton second as it is. It must be 15 Newton second with the direction of the impulse. The direction is important because without including direction, you start losing marks, and we do not want to lose those marks. You don't want to lose free marks. You don't want to lose marks of not putting in the SI unit. You don't want to lose marks for not just putting in direction. You must always remember, impulse is one of those examples of vector quantities. The same vector quantities that we spoke of in your grade 10 class. Okay. Right. So, again, we're saying we're defining impulse as the product of the net force acting on an object and the time that the net force acts on an object. I should say that this definition was taken from the exam guideline word for word, which is what I usually advise learners to do. To say when you are defining, you must only define according to the examination guideline. And you define according to the examination guideline word for word. What we don't do is define according to our own understanding. We don't define according to our own understanding, and we don't define according to external sources. We define according to the examination guideline. You explain according to your understanding. If you want to use your understanding, you use it when you have to do what? Explanation questions. But you do not define according to your understanding. You define according to the examination guideline. Hence, I have taken this definition from the examination guideline word for word. The product of the net force acting on an object and the time the net force acts on an object. Okay. Right. So, grade 12, it is said that the impulse is equals to the change in momentum of an object. This is where momentum comes in now. If you remember at the beginning of the lesson, we said we are doing impulse and momentum. The same momentum that we have touched on during our previous lesson. If you remember, we said that change in momentum is given by mvf minus vi. If you remember from last week, this is our change in momentum. So it is said that the impulse on an object is equals to the change in momentum of that particular object. They are equivalent. They are equal. They are equivalent or equal. Impulse is equal to the what? To the change in momentum. It is equal to the change in momentum. Now, when we say impulse is equal to the change in momentum, grade 12, we are not saying impulse is change in momentum. They are not one and the same thing. One is the product of the force acting on an object and the time. So one talks about how much the force is acting on an object and the time, while the other one talks about the change in velocity of a particular mass, right? So the other one is a change in momentum, the other one is impulse. They are not one and the same thing, but they are equivalent in terms of their magnitude. So that means if I were to calculate the impulse of a certain object, right, and I find it to be 5 Newton second, the impulse of a certain object, and then I calculate the change in momentum of that particular object, again, I will find it to be what? 5 kilograms meters per second, as I found this one to be 5 Newton second, not the joules I was talking about, Newton second. So the amount or the magnitude of the two is going to be the same, but I cannot use the same unit for both of them. For change in momentum, I only have to use kilograms meters per second, while for impulse, I only have to use Newton second. I cannot say for impulse now I'm using kilograms meters per second. That's change in momentum. They are equivalent in terms of their magnitude, but they are not exactly one and the same thing. They are equal. Impulse is equals to the change in momentum. Knowing this concept is very important, Prito. Knowing that the impulse is equals to the change in momentum is going to help you a lot in working out a lot of questions there in question 3 or question 4 of your final exam. Okay, so if we say impulse is equals to the change in momentum, then we can again represent both these things mathematically, right? We know, as we have said in a previous slide, that impulse is equals to the net force change in time, right? And again, last week we said, as we have written here, the change in momentum is equals to mvf minus vi. So what we are essentially saying here is that this guy here, the impulse, is equals to this guy here. So we can write and say impulse is equals to delta p. But we already know that the impulse is what? F net delta t, as previously discussed in the previous slide. So impulse is F net delta t. So instead of impulse, I can write F net delta t is equals to delta p, which I will further expand as F net delta t is equals to m open bracket vf minus vi, or mvf minus mvi, as an expanded form of this formula. Now, once we have it like this, we now call it a what? Impulse momentum theorem. And the impulse momentum theorem tells us that the impulse of an object is equals to the change in momentum of that particular object. But luckily for us, we will never be asked to define or state the impulse momentum theorem. What we must be able to do is apply it in maybe doing calculations, determining the force, determining the time, or even determining the initial or the final velocity of that particular object, as long as we understand the relationship between the two. And the relationship is that they are equivalent. The relationship is that they are equal. Impulse is equal to the change in momentum. I will repeat again, impulse is equals to the change in momentum. It is very important to me that you understand that impulse is equals to the change in momentum, because without understanding this, you are going to be losing a lot of marks, and the marks that you are losing are free and very simple marks to get. Okay. Right. Now, when you take the same formula, which is F net is equals F net delta t, is equals to delta p, and you rearrange this formula by dividing on both sides by delta t, just simply doing the maths, divide on both sides by delta t, you are going to find that F net is equals to delta p over delta t, so that this formula can be rearranged and written like this. In maths, they say we're making F net the subject of the formula. So if you make F net the subject of the formula, you should arrive in a rearranged formula like this, where it now says F net is equals to delta p over delta t. Okay, this again must remind you of something. We talked of Newton's second law. If you remember Newton's second law, F net is equals to ma. But now we are finding again that F net is equals to delta p over delta t. So that it means that this and this are one and the same thing, right? Hence, this law after it has been rearranged in this manner, we now start calling it Newton's second law in terms of momentum. Newton's second law in terms of momentum is one of the laws that you must be able to state. So you state Newton's second law in two ways. You state Newton's second law according to the way it was stated in the previous lesson, where we say when a net or resultant force is applied to an object of mass m, it accelerates the object in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass of the object, right? You can state it like that. Sometimes you will be asked to state it in terms of momentum. In that way, you would have to say the net or resultant force acting on an object is equal to the rate of change of momentum of the object in the direction of the net force. Repeat, the net or resultant force acting on an object is equal to the rate of change. So it is equals to how fast or how slow the momentum of the object changes. That's what we mean by when we say the rate of change. We are looking at how long does it take the object to change its momentum. So if the object changes its momentum very, very quickly, it's because of the net force. If the object changes its momentum very, very slowly, again, it's because of the net force that is on that particular object. So it says the net or resultant force acting on an object is equal to the rate of change of momentum of that object in the direction of the net force. It is one of those laws that we must be able to state, grade 12. It is important that we are able to state Newton's second law in terms of momentum. All right. Okay. This relationship not only tells us about Newton's second law in terms of momentum, but it also tells us about the relationship of impulse, or the relationship in impulse of the force, the time, and the change in momentum. As to say, again, we go back on the egg. What actually causes the egg to break? If we say F net is equals to delta P over delta T, right? Or proportional. I'll put it as proportional because now I'm talking relationship, right? It's proportional to the rate of change of the momentum, right? So what we are saying here, it clearly shows that these two are inversely proportional to one another, right? The net force and the time. And when I say they are inversely proportional to one another, that then tells me if one of them increases, if the delta T increases, right? Let's not even say if one of them, if the delta T, because the other depends on the other. The net force depends on the time. The net force depends on the time. So if delta T increases, the net force is going to do what? Is going to decrease. The net force will always depend on the time. So if the time decreases, what's going to happen to the net force? The net force will always do what? Will always increase. So sometimes we explain these things, grade 12, and someone is listening and is thinking, what is this person saying? I'm going to try and put numbers to these things. And I hope if I put numbers, it makes sense to what I'm saying when I say if this one increases, this one decreases, right? We are keeping, remember in experiment, when you're doing an experiment, there are certain variables that you want to keep constant or fix them, right? So we're going to keep the change in momentum. We're going to say the momentum of this object changes the same way. However, the time it takes for it to change is the one that is different. So we're going to find out the relationship between time. So I'm going to need to write it as F net is equals to delta P over delta T. Okay, right. So I want you to think, if my change in momentum is 2, okay, my change in momentum is what? Is 2. And I say 2 over 1, right? What is going to be the answer? The answer is going to be what? 2 newtons. That's the force that I would have, right? Okay, what if I increase now? Which now is going to be what? 2 over 2. I am increasing the time of contact. If I increase it 2 over 2, what happens? Now I get what? 1 newtons. Okay? Let me increase again. Let me have 2 over 4. If I have 2 over 4, what's happening to my force? My force is turning to what? 0.5. 0.5 newtons. So let's check. What is actually happening to my force here as I increase the time? The time was 1 second, the force was 2 newton. Time became 2 seconds, the force is 1 newton. So the force is doing what? Is decreasing. Time was 4 seconds, the force became 0.5. So the more I increase the time, the lesser the force becomes. So the force depends on the time. That's what I'm trying to show you, that the force depends on what? On the time of contact. If you increase the time of contact, you do what? You decrease the force that is going to be what? Or the net force that is going to be exerted on that object. As you can see here, if we started from 1, we increase from 1 to 2. We keep on increasing the time of contact. What happens to the force? It decreased from 2 to 1. We increase the time of contact to 4. What happens to the net force? It decreases again from 1 to 0.5. So the more we increase the time, the more we are going to be decreasing the what? The force. And it actually works the other way around. If we can have F net is equals to delta P over delta T. And we say our delta T is 2 again, keeping it constant. And we said, as we said, we'll keep it constant, right? Now, let's start by 2 over 2, right? What are we going to be having? We are going to have 1. 1 newton is going to be our force if it takes 2 seconds, okay? Now, let's decrease the time and say 2 over 1, right? The 2 over 1 second, we are decreasing the time. What happens to the force? The force is going to go up to what? To 2 newtons. Okay? Let's say the same 2 over 0.5 over 0.5 seconds. Right? If we say 2 over 0.5 seconds, what are we going to get? We are going to get 4 newtons. Right? As you can see, if we decrease the time, what happens to the force? The force keeps on increasing. These are my forces. If we decrease the time, the force keeps on increasing. The force depends on the time. It's very, very important that we understand. Again, don't forget, we're trying to understand why is it that nowadays cars are weaker, or they are not as rigid as the olden day cars, right? And so far, we are finding that there is a relationship between the amount of time a force is exerted, right? Or the amount of time it takes for the object to change its momentum, and the force then that is going to be what? That is going to be exerted. We are saying the net force is going to depend on the amount of time it takes the object to come to a what? To come to a stop. This is giving us an idea. It is giving us a picture as to what is the reason these cars are now weak while the other ones were used to be what? They used to be strong. Right. Okay. This again now takes me back to my cars again. Impulse crumple zones. Right? So we used to have an old Toyota Cressida, which was rigid, very tough. You can lean against it. What you get? Even if it was involved in an accident, easy to fix because it does not crash or break as much. However, if you get involved in an accident driving a new car such as a Polo, right, chances are high that you are going to be paying a lot to fix that car because it's going to crash. Most of the time they crash to a point of no return where they are completely unfixable. Why is it? These people are not trying to save money by making these bonnets and these fenders and these bumpers to be what? To be softer, right? They are not trying to make or to save money by making them to be softer or using weak material as it was back in the day to say now these cars are fake. That's not the reason, great friend. The reason again is what is impulse, as was the case with the egg. If you drop the egg on the hard surface, it breaks. If you drop the egg on the softer surface, it does not break. So these places here on these cars that are soft, that are easily breakable or crushable, these places are called crumple zones. So we have these places that are called what? Crumple zones. That's what we call these places. They are there on purpose. They put there on purpose. Why do we put crumple zones on cars? Crumple zones on cars are put there for what? For safety of drivers and passengers. They are there for safety of the drivers and the passengers in the car. So the engineers realized that when they were having these strong cars, the likes of the Toyota Cressidas, right? Okay, when these cars are involved in accident, yes, these cars, they do not get damaged, but people are suffering, people are getting injured, and we are having more and more fatal injuries, which means these are the injuries that result in sometimes people passing away because of these cars. But then they realize that we have impulse, or the reason why this is happening is impulse. When these people are in these cars, the force that gets exerted on them during an accident is too big, right? And what makes it to be too big? It's because the cars takes a very little time to come to a stop. So a Cressida, when it hits maybe against a wall, or let's say it hits against a pole, a Cressida will simply hit the pole and simply come to a stop very quickly. If that happens, as we have discussed, according to this relationship, if it stops very quickly, then it means the force that is going to be exerted on the Cressida is going to be very, very high. And if the force that is exerted on the Cressida is high, then the force that is going to be exerted on the driver or the passenger in the car is going to be high as well. This is going to lead to fatal injuries, right? So what are we designing the polos to do? We are saying polo, say you are hitting a pole, right? A very strong pole that is not going to move. The polo is going to hit the pole, and the polo is going to crumple, right? It's going to crumple, allowing the pole to sort of come in or get in the pole, crush it. So it allows it to crash. So the cars are designed so that they crash during impact. It's important that they must crash. When the car crashes, it's going to save the passenger and it's going to save the driver. How so? When the car crashes, the time it will take for the car to come to a complete stop will increase. So it's not going to simply stop like the other car, the car with a rigid bumper, a rigid body, right? It's going to take some time for it to stop while it is crashing, while it is getting destroyed, right? It has not exactly stopped. So it is taking time for it to come to a what? A complete stop. Once it stops, the force that is now exerted on the car will be lesser than the force that would have been exerted if the car did not take that much time. As we say again, we refer to our relationship. If the time increases, then the force that is exerted is going to do what? Is going to decrease. That's why nowadays cars are going to be soft. These soft places that are on our nowadays cars, we call them crumple zones. Crumple zones are safety features in cars. Crumple zones are there to protect the drivers. They are there to protect the passengers. They are there to protect and eliminate or decrease the amount of fatal injuries that are experienced in roads when people are involved in accident. These cars are designed so that they must what? They must crash. As they crash, they do what? They increase the time of contact. As the egg, or as was happening with the egg on the cushion, the egg had a greater time of contact with the cushion, helping it to do what? Not to break. The same thing is going to happen with the nowadays cars. They will have a greater time for them to come to a stop, which means a greater time of contact. The greater time of contact will lead to less net force exerted on the car, hence protecting the driver or the passenger in the car. Okay, so let us take an example and try to solve this using calculations, to see if we have a car with a rigid bumper versus a car with a crumpled zone, right? Which one is going to experience a greater amount of force? Okay, so example 1 says, to improve the safety of motorists, modern cars are built so that the front end crumbles upon impact, right? Exactly what I was saying. They are built so that they must crumple if there is impact, if there is an accident. They must crumple, okay? A 1,200 kilogram car is traveling at a constant velocity of 8 meters per second. It hits a wall and comes to a complete stop. Comes to a complete stop. As you see there highlighted in red, complete stop. It's a keyword there. And keywords have implication. You must know what it means when it says it comes to a complete stop in 0.25 seconds. So let's try and maybe have some sort of a diagram of what is happening here. We are having our car here, and our car is moving with a velocity of 8 meters per second. And it's going to hit a wall. And when it hits the wall, it is said that it will come to a what? A complete stop. We are asked to calculate the net force exerted on the what? On the car, right? Okay, so if they say calculate the net force exerted on the car, how are we going to do that? Well, the best way to answer this question, grade 12, is to go back to what? To knowing that the change in momentum is equal to what? To the impulse. Because if you think about it, I cannot jump to this formula. Impulse is equal to F net delta T. This is going to be difficult. Why? Because I do not have the impulse of the car yet, and I do not have the net force. So I end up having two unknowns there, right? So what do? Well, if I know the initial velocity of the car, and the car hits the wall and comes to a stop, that tells me its velocity has changed. And last week, what did we say? If the velocity of an object changes, its momentum does what? Changes with it, or changes as well. So if I know that the car had an initial velocity of 8 meters per second, I know its mass, and I also know that it's going to have a final velocity of 0 meters per second as it comes to a what? A complete stop. Then I know that the car changes momentum. I can calculate the change in momentum. What do I do with the change in momentum? Have to remember, as I said, very, very important for you to remember, grade 12 learner, that the change in momentum is equals to the impulse on an object. So once I have that, I can then simply write this formula like this. But before I write the formula, I must take direction, as we have spoken last week. Anything that has momentum in it, direction must be taken. So since I'm saying I'm going to be using the change in momentum, then that means I must take direction. Okay? So I'm going to say take direction of motion as positive. Wherever the car is going, it's going to be positive. And wherever the opposition of that must be negative. So the direction of motion will be taken as positive. Then I'll write my formula. F net delta T is equals to delta P, which can be expanded as F net delta T is equals to M VF minus VI. Once you have done this, you have won the battle. It's very, very simple. You will now start doing what? You simply substitute. I am looking for the net force. The net force multiplied by the time of contact. I usually say to learners, immediately you hear they say it takes this time to come to a stop, or the time of contact is this, you must always think of this momentum impulse theorem or impulse momentum theorem. Okay, right. So our change in time is 0.25 equals to the mass of 1,200 kilograms, right, into the final velocity of what? What is our final velocity? It comes to a complete stop. Therefore, its final velocity must be 0 meters per second. Keywords, grade 12, and keywords have implication. Once they tell us it comes to a complete stop, that's a keyword right there. Its implication is that its velocity is 0. At rest, that's a keyword right there. Its implication is that the velocity is 0, and then stationary, again a keyword, implying that velocity is 0. Knowing keywords is very, very important, and knowing their implication. So the final velocity of the car will be 0 since the car comes to a complete stop. When something is stopped, it's not moving, it cannot be having a velocity greater than 0. Right. And initial velocity was that of 8 meters per second, and it was in the direction of the motion, and the direction of the motion is positive. So I'll substitute it as positive there, and then I will divide by 0.25, divide by 0.25, right? This will cancel this, and that I will find that the net force that is exerted on an object, take my calculator, and I will say fraction sign, 1200, open a bracket, 0 minus 8, close the bracket, all over 0.25. This is equals to, I get my answer as a negative 38,400 newtons, right? Now I cannot leave my answer as a negative 38,000 because negative is not scientific, it's a mathematical symbol. Yes, it symbolizes the direction which is in the negative direction, but scientifically it must be written in words that 38,400 newtons faces in the opposite direction. In the opposite direction, since we said the direction was positive, therefore the opposite must be the negative one. Opposite direction of motion. Right, that is the net force that is exerted on the car, right? Because they said calculate the net force exerted on the car. Okay, now after doing the calculation, I usually advise people to ask this very important question here. Does it make sense? This is what you ask yourself after you get your answer, especially when you are doing an impulse momentum question. You must ask yourself, does it make sense? And what are we asking? We are asking in terms of the direction of the force that you have been asked to calculate, right? You are getting a force and they are saying it is 38,400 newtons in the opposite direction of motion. And the question is, does it make sense that the force must be in the opposite direction of motion? And the answer to that question would be yes, because if the car goes in a direction of motion and hits the wall, it will exert a force in the direction of motion. And according to Newton's third law of motion that we've discussed previously, we said the wall, as the car exerts a force on the wall will exert simultaneously, by the way, simultaneously exert a force of equal magnitude, right, on the car. So the force will be equal, but it will be in the opposite direction. So therefore, the force that will be exerted by the car is 38,400 newtons, and it is in the opposite direction. Therefore, my answer is correct and it makes sense. But if I had found that the answer was positive, it was in the direction of motion, then that cannot be making sense to me, because the car cannot experience a force in the direction where it is exerting a force. It must experience a force in the opposite direction. Okay, so we are finding that the force exerted on the car with a crumple zone, right? A crumple zone is 38,400. Okay, let's try and find the force exerted on the car without a crumple zone now, right? The question says here, determine the net force exerted if the same car, right? We're having the same car now, had a rigid bumper and stopped in 0.040 seconds. You will notice that the time of contact has changed from 0.25 to 0.04 seconds. The time of contact has actually decreased, right? So already before we do the calculation, we should be having an expectation. So again, we are going to take direction of motion as positive. You cannot do a calculation that involves momentum without indicating direction and underlining. You must always indicate direction and underline. Right, so we're going to write our formula. F net delta T is equals to delta P, impulse momentum theory. F net delta T is equals to mvf minus vi. Simply substitute now, right? We are looking for the F net. we do have the time. It has changed, drastically decreased because of the reached bumper now. Takes less time to come to a stop. We will see if that is safe. Right, the mass of the car was 1,200, a final velocity of 0 since it comes to a complete stop, and an initial velocity of 8 meters per second. Now we divide by 0.040, divide by 0.040. This will cancel this, and we'll get that our net force is equals to, quickly run to our calculator, 1,200, open bracket 0 minus 8, close the bracket, all over 0.040. This should give us negative 240,000 newtons from, if you remember, 88,400 newtons in the previous slide. The car with, well, we're not done. We're now going to write this as 240,000 newtons, again in the opposite direction of motion. We must indicate it with direction in weights, not direction in symbols. We're not allowed to do that. Okay, so now let's look at it. First question before we continue, does it make sense in terms of the direction? Yes, again, it makes sense that if the car was moving in the direction of motion, and that direction of motion we took it as positive, then the force that is experienced by the car should be in the negative direction after it has crashed or as it crashes. Okay, but again, now we have to compare. If you remember, we are comparing, we are trying to find out, is it true mathematically that it is safer to be in a crash or involved in a crash where a car has a crumple zone, or involved in a crash where a car has a rigid bumper? By the numbers, or looking at the numbers, the force that is going to be exerted on the car if it has a rigid bumper is 240,000 newton, while the force that is exerted on the car that has crumple zone is only 38,400 newtons. You can see the difference between the forces. The difference is huge. The difference between the two forces is huge. A car with a crumple zone makes it much safer on impact than a car that has rigid bumpers. That's the reason why, again, we are talking about why are these cars becoming softer, or why are they making them softer. It is not to save money. It's not being economical. It is to save people's lives. It is to decrease fatal injuries, because if they are involved in an impact, if the car is rigid, the net force will be high. What will be causing the net force to be high? It's because the time of contact will be less. Smaller time of contact, higher net force. Okay, and higher time of contact, lower net force, as was the case in the car with a crumple zone, as we can see in the car that does not have a crumple zone. The second question there is saying, without doing any calculation, write down the force exerted on the wall. Right? We have been calculating the forces that is exerted on the car, experienced by the car. We are saying it is 240 newtons in the opposite direction of motion. So the force that will be exerted on the wall, as I try to fit it in here, it's going to be 240,000 newtons in the direction of motion. And how do I get this answer? Again, as I explained in the previous slide, as the car approaches and hits the wall, it approaches in the direction of motion. Therefore, the car will exert a force in the direction in which it is approaching, right? The wall will exert a force in the opposite direction. And these two forces must be equal in magnitude, opposite in direction. This is according to Newton's third law of motion. That's why the force on the car is 240,000, opposite direction of motion, while the force on the wall is 240,000 in the direction of motion. I hope this gives an understanding as to why these cars are having crumple zones. And I hope the issue of crumple zones in cars is sticking in your head, grade 12 learner, that cars have crumple zones as safety features. They are there to eliminate fatal injuries by increasing the time of contact during impact, hence decreasing the net force exerted on the car. Okay, so it is not only crumple zones that are in cars that have the safety features, right? We also have things that are called airbags. Airbags, right? We've seen in these new cars. Again, if we compare them to olden day cars do not have airbags. The best thing they have is a seat belt, right? Which is a safety feature, yes, but nowadays cars, they also have airbags. What are the airbags there to do? Well, you would notice that, yes, when you are in a car, even if the car has a crumple zone, it will decrease the force that is acting on the car, right? But you are a human being. You are more fragile and more softer than the metal that is used to make a what? A car. If you happen to move according to Newton's first law of motion, if you would remember, you continue in your state of motion, right? Uniform motion, right? If you happen to continue in that state of uniform motion, you would eventually maybe hit either the dashboard or hit the steering wheel, right? And this is not good or safer for you, right? To make it much safer, they designed airbags, okay? What are these? What are airbags? Well, airbags are these sort of balloonish things that pop out during an impact. They pop out and they inflate, okay? Well, they inflate, and then when you come and you hit, instead of hitting on the steering wheel, you will hit this inflated balloon, which is an airbag, and you hit it. And as you hit this inflated balloon, its job is to, after you hit it, it must do what? It must deflate. So it must immediately, when you hit it, it deflates. So what is it actually doing when it deflates? What it is doing is increasing the time for you to come to a stop. So the time that you take to come to a stop increases as the airbag is doing what? Is deflating. So the deflation on the airbag helps us by increasing the what? The time of contact. So it takes time for you to what? To come to a stop, and this reduces the what? It reduces the force. These are questions that would be asked in your exam grade 12, where you'll be expected to answer these questions. And the best way for you to ask them or to answer them is to understand that most of the time when these questions are asked, again, we must fix something. We are going to be fixing the change in momentum, because we'll be comparing maybe a car that has the same initial velocity and the same final velocity. So it will have the same change in momentum. So if we have the same change in momentum, if we increase the time of contact, an increase in the time of contact will do what? Will decrease the net force. We've been saying this for the whole lesson now. The whole lesson today, we've been saying the same thing. If you increase the time of contact, you will decrease the net force exerted. And the opposite is true as well. If you decrease the time of contact, you will increase the net force exerted on the object. But the idea behind the safety features is that they must do what? They must increase the time of contact, so that when we are having that change in momentum that we are having, and we are having an increase now time of contact, then this is going to do what? Decrease the force that is exerted on a particular object. And in cars, that object will be what? Will be a human being, a driver or a passenger, helping you to survive, increasing the chances of you surviving, decreasing fatal injuries, and increasing road safety. So that's one of the things. So engineers have designed crumple zones in cars, right? But they've also designed airbags. So now we're having more things that are designed to help drivers or to help drivers and passengers, right? So that they do not succumb to death during impact or during accidents. Okay, right? What else can be used as a safety feature in roads? Well, in roads, there is something called an arrestor belt. Okay, now this one here is not a safety feature on the car. Okay, for people who have traveled maybe long distances, highways or national roads, you will see a sign that looks something like this on the roads. You will see a sign that looks something like, some of you will recognize it will have a red, a white, a red, a white. It is something that, a sign that looks something like this: red, white, red, white. Okay, right? This sign symbolizes a what? An arrestor belt. This sign symbolizes an arrestor bed. So what is an arrestor bed? An arrestor bed is a certain portion, right, on the road or next to the road. It is put next to the road where they are going to create a certain portion for cars that maybe have run out of brakes, right? They are now moving without brakes. They cannot stop. It's difficult for them to stop. So instead of these cars crashing maybe on huge rocks or crashing on other cars, on crashing on maybe the road walls, the walls next to the road, they are given this space where they can enter, right? And then this space will allow the car to do what? To just eventually come to a stop. So what's the difference between this place and the road? As you can see here, this place here has what? It has sand. They put sand in here, okay? Unlike the road, which is tarred, right? The road is tarred. Here they put sand. Why are they putting sand here? So when you put your car in this sand, what this is going to do, it's going to increase the time of contact between the tires, right, and the sand itself, okay? So an arrestor bed does what? It increases the friction, So as there's more time between the tires and the sand, the frictional force that is experienced by the car is going to increase. So the sand will increase that time or increase that friction. And as it increases the friction, it will also be increasing what? The time it takes for your car to come to a stop. Usually this is designed for, most of the time, it's for trucks, big trucks. And you would find it in steeper roads, right? As the truck is going down the steep. And then next to the steep, you will see there in the road, there will be an arrestor bed to say if the car happens to lose brakes while it is on that steep road, it's the truck's driver's responsibility to then what? To direct the truck to go to an arrestor bed where he will be increasing the time of contact between the tires and the sand, hence increasing the friction, hence increasing the time of contact. As it increases the time of contact, then the force that will be exerted when the car eventually comes to a stop will drastically be reduced. So this makes it safer for truck drivers. It makes it safer for even every driver on the road, because it's not necessarily for truck drivers, but it's mostly for truck drivers. To say, as you can see there, it says truck arrestor bed. Most of the time they are designed for trucks because trucks are bigger cars. They are difficult to stop. And these are the cars that will find they will fail, they will have brakes failure most. So the truck is having a failure, go into an arrestor bed, and what is the arrestor bed going to do? Well, the sand there will increase the friction, right? Because there will be more contact between the sand and the tires themselves. So the friction increases there. And when the friction gets increased, right, that means the time it takes for the truck to come to a complete stop also increases. Then that means the force is going to be less. Again, we are still talking that relationship. We've been talking the whole lesson. We are saying if the time of contact is high, the force is going to be low. If the time of contact is low, the force is going to be high. This is impulse momentum theorem. This is for us to be able to do what? To do the calculations, and also to be able to what? To explain as to why the force was big or why the force was what? Small. But we must also be able to what? To do the calculations, right? As we see in the following example. Okay, so we're going to take an activity here, right? And the activity is that a 150 grams tennis ball strikes a wall at a velocity of 20 meters per second and bounces back in the opposite direction at a velocity of 16 meters per second. And we are asked to calculate the impulse on the ball. Okay, this question here is very, very important, okay, because I want you to think about it. They're saying 150 grams tennis ball, it strikes the wall 120 meters per second, comes back 16 meters per second. Okay, to make it easier for myself, I'm going to try and draw this scenario. So I'm going to put myself a wall here, and then I'm going to have a what? The ball. And then I'm going to say this ball will be moving in this direction, 20 meters per second, right? And then I know that it is going to go hit here, and then it will come back. At some point it will be around here after it has hit the wall, and then it will be now moving with a velocity of 16 meters per second. Okay, this is 150 grams ball. Okay, so what's the first thing that I notice? Well, I should notice that this is given in terms of what? Of grams. And my SI unit for mass is what? Is kilograms. So the first thing that I must be thinking to myself is that I must convert this mass from grams to kilograms by doing 150 times 10 to the power of negative 3. Or for some of you, it's 150 divided by 1,000. Whichever one you use, it's fine. Okay, you are going to get that your mass is 0.15 kilograms. Your mass is going to be 0.15 kilograms. Okay, but now we have another problem. They are saying calculate the impulse. And if I remember, the formula for impulse was impulse is equals to F net delta T. But look at the question itself. They have not told me anything about the net force. They have not told me anything about the time of contact. So how am I expected to calculate impulse? This again, grade 12, brings me back to that point where I say understanding that change in momentum is equals to the impulse is very important, because such questions are going to come. Such questions will be asked where you are expected to calculate the impulse, but you have no force, you have no time of contact, and these are usually the questions that are asked. So how do you go about doing that? What you need to do is realize that the change in momentum is equals to the what? The impulse. They are equivalent as we have spoken. So that means I can simply calculate the change in momentum, then I'll have the value of the what? Of the impulse. So to do that, again, I must do what? Take direction, because I am dealing with momentum. So I'll say take a direction of motion as positive. Taking the direction of motion as positive. Okay, take the direction of motion as positive. Then from there, I write the formula. Delta P is equals to mVF minus VI. Then from there, I do what? I substitute. What is my mass? My mass is 0.15 kilograms, converted from 150 times 10 to the power minus 3. By the way, you can just substitute it here as times 10 to the power minus 3 here if you want. It will make life easier for yourself if that's the case. And then final velocity is 16 meters per second. But the 16 meters per second is moving in the opposite direction. So it must be a negative 16 because it's in the opposite direction, minus a positive 20 meters per second. Then straight to my calculator, 0.15, open a bracket, negative 16 minus 20. And then I'll get that the change in momentum is negative 5.4 kilograms meters per second. Okay, not even going to stress myself by writing 5.4 kilograms meters per second opposite direction of motion. Why? Because I'm not calculating change in momentum. I've been asked to calculate impulse, right? They might be equivalent, but again, they are not one and the same thing. So what I will do here is I will say, to conclude, the impulse which I was asked to calculate is equals to 5.4 in magnitude Newton second, because I am calculating the impulse. Newton second in the opposite, because it was negative, in the opposite direction of motion. It was very important for me to do this question, grade 12, because I want to show you that when you are asked to calculate the impulse, or you can be asked to calculate the impulse and be expected to use the change in momentum, and most of the time that's going to be the case. But that means, again, the other side is correct as well. You can be asked to calculate the change in momentum, giving information on what? on impulse. That one is rare. The one that is mostly asked is the one where we calculate the what? The impulse, giving the information of how the momentum of the object change. So we must not stress. We must not start thinking, what do they expect me to do? We must just simply remember that the impulse is equal to the change in momentum of an object. Therefore, you can use the change in momentum of an object to calculate the impulse of that particular object. Okay, so as we continue, right, we're continuing with our activity. Here's an activity which was taken from a previous question paper, right? They say here, cats can land on their feet when they fall from a tree or a roof. The diagram below shows the general movement of a cat with a mass of 3.8 meters per second as it falls from a tree. Okay, it takes the cat 0.25 seconds to come to a standstill. Time of contact. I make note. I see this. I think F net delta T is equals to delta P immediately. Okay, I think of that immediately. Okay, it takes 0.25 seconds to come to a standstill on the ground with a velocity of what? 4 meters per second, right? So it takes it 0.2 seconds to come to a standstill on the ground. So it takes 0.2 seconds for it to come to a standstill. So it was moving with a velocity of what? 4 meters per second as it was falling. First question there tells us define the term impulse. Okay, and the next question is asking calculate the magnitude of the average force that the cat experiences when it lands. Okay, so therefore, to answer the first question, define the term impulse, we're going to say impulse is the product of the net force acting on an object and the time the net force acts on an object, defining there according or exactly according to the examination guideline. It is the product of the net force acting on an object and the time the net force acts on an object. All right, let's try and do the calculation one. As you can see here, here's our definition. The product of the net force acting on an object and the time the net force acts on an object. Okay, but they also wanted us to calculate the what? The force that is exerted on the cat as it falls. So how do we do that? Well, I've collected data here because it was in the previous slide. We are saying we know the mass of the cat is 3.8 kilograms. We know that the initial velocity or the velocity the cat was moving with before it came to a standstill, which again was a keyword there, came to a standstill, meaning that it's no longer moving, so it comes to a stop. The velocity there was 4 meters per second initially, and the final velocity has to be what? 0, since the cat comes to what? A standstill. And how long does it take for that to happen? 0.25 seconds for the cat. So we are talking about now the collision between the cat and the ground. The collision takes about 0.25 seconds, and we are asked to calculate the force that the ground is going to exert on the cat. They say calculate the magnitude of the average force that the cat experiences when it lands. So we're looking for the force that the ground is going to exert on the cat. Very, very important to know what force are you calculating. The force that the ground is going to exert on the cat, because average force that the cat experiences. So it's the force on the cat. Okay, so we're looking for the force on the cat. So what do? We start by saying we know that the change in momentum must be equal to the impulse, but we need direction. So we are having an up and down movement here from the diagram itself. You can see the cat is falling, so it means we are having a what? An up and down movement there. So how do we take our direction? I would say take upwards as positive. It is very simple and easy for me to take things that are going up as positive, because I can relate these to maths, the Cartesian plane. I can relate this to the Cartesian plane to say whenever something goes up in the Cartesian plane, those numbers are positive. The down numbers are negative. The right numbers are positive. The left numbers are negative. For me, it makes it very, very simple. But we must remember that taking direction is up to an individual. Okay, then from there, I would say F net delta T is equals to delta P. Okay, And then I expand that. F net delta T is equals to M VF minus VI. Okay, and then from there, I start substituting. I am looking for the force on the cat. The time it takes is 0.25 equals to, what is the mass of the cat? The mass of the cat is 3.8 kilograms, and the final velocity, the cat comes to a standstill, so its final velocity must be 0, minus the initial velocity of 4 meters per second. So the initial velocity there is a minus 4. Why minus 4? The cat was moving down, and we just said we are taking upwards as positive. So the cat was moving down, it was falling down. So its initial velocity was negative. Therefore, we are going to solve for F net by dividing by 0.25, dividing by 0.25. Then this will cancel this. The F net would be equals to 3.8, open bracket 0, minus a negative 4, close the bracket, all over 0.25. You get that the force, or the net force, is 60.8 newtons, and since it's positive, it is upwards. Okay, before I ask my question here, I want to go back here with the issue of direction, right, just in case someone did not understand. Remember, grade 12, velocity is a vector. It has magnitude and direction. When the cat was falling, it was falling going down, and we have taken a direction saying upwards is positive. So if upwards is positive and the cat goes down, that means its velocity is going in the negative direction. So if it's going in a negative direction, then this 4 must be what? Must be substituted as a negative. Okay, that's why I'm substituting this 4 as a negative there. So the F net becomes 60.8 newtons upwards. Then I ask my famous question: does it make sense? Does it make sense that the force that will be experienced by the cat is positive? Does it make sense that the force experienced by the cat is positive? According to how I have chosen my direction, the answer to that question is yes, it makes sense, because the cat is going down. It is going in a negative direction. That means the cat will exert a negative force on the floor in terms of how we have chosen the direction. By the way, remember, it's important. It is based on how you have chosen the direction. So the cat will exert a what? A negative force on the floor. Then the floor, or the ground, will have to exert a what? A positive force on the cat. So as the cat is going down, it exerts a negative force. Then when it hits the ground will then simultaneously exert an oppositely directed force of equal magnitude on the cat. According to Newton's third law, it must be positive. That force must be positive. It is very, very important that we ask ourselves that question: does it make sense? Because if we don't ask ourselves that question, we'll find out that maybe we get our answer as negative and we leave it like that. And in that case, that answer will not be correct, because it has to make sense. We have to say that it makes sense. It's in the direction where the force is exerted. Okay, right. So as you can see, right, the force that the cat experiences is not big. It's a small amount of force, right? Why? When cats are falling, if you have seen a cat fall, the cat falls and it's as if it goes down with its whole body, or allows its body to go down. So if you have noticed a cat fall, it does not fall and just stand still. It falls and allows its body to go down. If maybe you've seen people who do stunts, they are jumping from one building to another building. Those people do not jump straight. They don't jump and go and just stand straight. When they jump, they allow their body to almost fall and even touch the ground. Why are those people doing that? Why is the cat falling and almost go down with its whole body? right? Well, it seems our brain knows, it knows this science. It knows that if we increase the time of contact, we are going to do what? Decrease the net force. It seems like our brain, the brain of the cat, and even our brain, because even you as an individual, if I can throw you from a very, very high place, right, where you would survive, obviously, when you get to the ground, you will not just simply stand still, because your brain will tell you that it's going to hurt more if you just try to stand straight up. You will have to fall as if you are going with your whole body to the ground. Your brain will automatically try to tell you this. You do this, your brain will tell you to do this. It's as if the brain understands that impulse, right? That impulse, or impulse momentum theorem. It understands that we must increase the time of contact. So what the cat is doing there, as it falls and goes with its whole body down, it is increasing the time of contact between the ground and the cat itself. So as it increases the time of contact, the force that is acting on the cat is going to be less. That's why you find cats being able to jump from very, very high buildings or very high places, and they will never get hurt. They understand the impulse momentum theorem. They understand that they must, when they get to the ground, they must try to increase the time of contact as much as possible with the ground. That is going to minimize the force that is exerted on them, hence making it safer for them or helping them survive. So that's why you are seeing that the cat is only experiencing a small amount of force of just about 60.8 newtons. Not enough to do what? To hurt the cat. So that's what we also do. That's what these people are doing when they are doing this dance and they are jumping off high buildings. They jump and they go down with their knees. You see their knees bending there. They are bending their knees to do what? To increase the time of contact between themselves and the ground in which they are jumping, or on top of which they are jumping. They are increasing the time of contact. If they increase the time of contact, that is better for their legs and for their joints, because if they don't do that, the force is going to be high and it's going to hurt or even sometimes break their bones. So that's what they are avoiding. So that's what the cat is also doing there. So another thing that you can think of where the time of contact is increased or where we are having impulse. Right, as you can see there, here's our solutions in different options there. Or maybe sometimes you can start by calculating the impulse. These are when you take different directions, and we are all getting what? An answer of 60.8, as we also got here, an answer of 60.8. Yes, that's what we got. So the answer here is 60.8 as well, newtons. That's the force that is exerted on the cat itself. Okay, let's continue and take another example or activity, right? This one is a big one, okay? So we'll try and move faster, but without leaving people behind. This one says, a hard basketball of mass 620 grams, okay? Again, the mass is given in what? In grams here, so be careful. This must be converted. Hits the floor with a velocity of 16 meters per second, okay? The ball is in contact with the floor for 0.05 seconds, after which it bounces back at a velocity of 10 meters per second. So it will hit the floor and it is in contact with the floor from 0.05 seconds. Immediately, as I said before, immediately, I think F net delta T is equals to delta P. Please, Creator, please, immediately you must think like this. I like writing this formula like this, not the other way around where it was rearranged, F net is equals to. And the reason for that is because I know in the formula sheet, most of the time it is given like this in the during the final exam. So I like to write it like that as well and just do the working out after. Okay. After which it bounces back at a velocity of 10 meters per second. Again, number of interest here. An illustration of this is shown in the sketch below. So here's the sketch. You can see the ball going down. The initial velocity is 16 meters per second. Bounces, then goes up. The final velocity is 10 meters per second. Okay. The first question there says, define the term impulse. Let's define the term impulse. In grade 12, I warn that every time you are doing these activities, and every time you are starting with a question that says define or state. Let's not skip these questions. Let's not quickly rush to do the calculations, because what we tend to do as learners is that we skip. We say, it's define, you skip. No, always define. Always define, and as you define, you write it down and you speak it at the same time. This is going to help you to never forget it. So you will never have a point where you have to sit down before the examination and memorize definitions, because they will already be here in your head. So it's important that you always do it when you do these activities. Don't skip the definition. So define the term impulse. Impulse is the product of the net force acting on an object and the time the net force acts on an object. Very important. You know it like that from the examination guide 9. 3.2.2 says, calculate the force that the ball exerts on the floor. Okay, calculate the force that the ball exerts on the floor. Very important to know which force are we looking for. It's the one that is on the floor, exerted by the ball, so that we can be able to answer the question, does it make sense? Right, let's go and try and calculate that force. Okay, so we are going to start by taking direction. We would say take upwards as positive. I take upward as positive. Anything going up for me must be positive. Okay, we've done the definition. Okay, so, and then from here we are going to simply say F net delta T is equals to delta P. F net delta T is equals to mVF minus VI. Okay, F net. Now I'm gonna need to go back and take some data there. Okay, the time is 0.05 and the mass is 620 grams, and then I have 16 initial and 10 final. 0.05. Okay, so the time will be 0.05 here with a mass of 620 times 10 to the power minus 3. I'm already converting it to grams. Final velocity of 10 meters per second up with an initial velocity of negative 16, which is going down. Divide by 0.05, divide by 0.05. Cancel this, you get that F net is equals to fraction sign 620 times 10 to the power of a negative 3, open bracket 10 minus a negative 16, close the bracket, all over 0.05. I'll find that the force exerted is what? 322.4 newtons, right? But now we ask that question, does it make sense? And the answer to the question this time around is no, because they are looking for the force on the floor. We say up is positive, the force is positive. So this cannot be. So how do we deal with this issue? Well, we know according to Newton's third law of motion, simply that the force that will be exerted on the floor will be equal to the force exerted on the ball. So this 322.4 is the force exerted on the ball. Why are we calculating and getting the force exerted on the ball? Because we use the change in momentum of the ball. I hope we all understand that. Therefore, the F net is actually equals to 322.4 newtons downwards. That's according to Newton's third law of motion. That is according to Newton's third law of motion. Okay, then let's go back and check the other questions. They are asking what will be the magnitude and direction of the force that will be exerted on the ball. We've already calculated 322.4 newtons upwards. The contact time between the ball and the floor is increased. How will this affect the net force exerted on the ball, right? I'll just quickly go through that with you. If the contact time increases, right, the force is going to do what? Decrease. Give one feature of the application of impulse in road safety: crumple zones, airbag, safety belts. Grade 12. Thank you.